All right, let's see. Test, 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 test. All right, let's get started. This volume okay? If everybody gives me a second. All right, volume is okay? Not too loud, not too silent? I'll take that as a yes. All right, so welcome everybody. It's the last week of lectures. You're almost done. So today we're going to be talking about self-supervised learning. This is the first part. So on Friday we'll be also talking about self-supervised learning. Today we're mainly talking about self-supervised learning from a single modality, so from a single input source. And on Friday we'll be talking about self-supervised learning if you have two modalities, such as if you have a video, you typically have the audio stream and you have the video stream. Self-supervised learning already came up in a bunch of lectures. So we had it in the transfer learning part in lecture 5. We had it in lecture 7 when we were talking about transformers. Of course, in NLP, self-supervised learning is the main way how we learn representations, as well as we already talked about the attention maps that a visual transformer learns. We had the big BIGAN in lecture 10 as a representative of a sort of something that's in between an autoencoder and a generative model. And also, Andrea from Oxford mentioned the usage of the Dino self-supervised model for 3D learning. But not only that, we of course have, you guessed it, the learning outcomes. So, of course, it says here that the students can explain and motivate the fundamental principles and mechanisms behind deep learning's past, present, and future. And self-supervised learning is definitely a fundamental principle in the past, present, and future. So that's a check. And it's also a way to tackle the major challenges we have at the moment in deep learning, which is the labeled data, the biases in labels, and the scalability of the methods. And so in that sense, it fits quite well into these objectives. All right, so today's lecture will be covering these topics. I'll be giving an introduction about finally what is self-supervised learning. So Andrea teased about it, that we're going to learn about it. So now I'm going to give you sort of the more formal introduction to it. Then some reasons why would we want to do self-supervised learning and how to do it. And within this how to do it, we'll be deep diving into the data sets we'll use, the augmentations we'll be using, as well as the methodology. Also, one note here, as I've written in the bottom, is that this topic is really, really an active research field. And if you were to plot the number of publications in the last few years, it really skyrocketed. There's no proper textbook about this, so we'll be instead looking at some research papers. I'll be mostly focusing on research papers which I've written or co-written, because they give you a good sort of overview on the topics, because they cover some of these things that we'll be talking about, and I'll be able to answer the questions, I hope, to the best satisfaction. All right, let's start with the what of self-supervised learning. If you also recall lecture 1 where we talked about the history of deep learning, we sort of had this general image, right? Like we had the new algorithms starting from Rosenblatt and then moving on to CNNs. We had this new capacity to do matrix multiplies really quickly thanks to GPUs. And then the thing that we hadn't mentioned all that much, except that we were improving on ImageNet, was this data. This rapid rise in large-scale data sets was actually the fuel, if you so will, for this whole deep learning revolution. And the other parts were basically the motor. However, when we think of normal supervised learning, this data is really made up of two parts. So you have, on the one hand, these images or videos or any kind of data, molecules even, that you generate, which are extremely cheap. But in supervised learning, you have this other side of the coin, if you so will. And for example, these are typically annotations, and these could be all kinds of things. So these could be, for example, just labels per image, like railroad crossing or trogon, which is already, as you can see, like a sort of not so common thing to know. It's a special bird. But it could be more detailed, such as bounding boxes around objects, or even pixel-wise annotations where you exactly show which pixel belongs to what object. And drawing these kinds of annotation maps can take 30 minutes per image if you want to be really precise. And of course, for applications like self-driving cars, you do want to be really precise. So the goal of self-supervised learning is basically to get rid of this whole right-hand side. It's really this part which is expensive, which is limiting, and which, if you think about how humans develop, we, especially as toddlers where the main visual system develops, we surely don't know what a trogon is. We don't need pixel-wise segmentations of our parent teaching us this pixel belongs to a duck and this pixel doesn't belong to a duck anymore, right? So clearly the way we learn in machine learning is not super aligned with how we learn normally. And so what we want to instead do is have the data provide us with a supervision signal. And this is the rough definition of self-supervision. We'll go into a more detailed definition later. But this is sort of the graphic that we'll be looking at. So you see the images, sort of, then you have some sort of self-supervision signal, and you do something with those images. And you do something is usually the thing that we need, which is getting a gradient to train these neural networks. And with that, the general procedure looks as follows. We have two steps. The first step is the pre-training stage. So as I said, you have this unlabeled data set, and you apply transformations. Transformations are just a different word for augmentations. And you have your deep neural network. This could be a vision transformer. This could be a convolutional neural network. Could be a graph neural network, anything really. And then you have something that I'll call proxy task. The important thing about the proxy task is that it doesn't require labels to give you gradients. And once you've done that, you have trained your deep neural network using those gradients. You can do something with that. And for the proxy task, usually we'll have something like geometry-based, clustering, contrastive, generative. We'll dive into a couple of these. Generative you've already had. So that's something, for example, like what the GAN is doing. The GAN is a generative objective. And especially if you have an encoder in the GAN, like we had in the big BiGAN, you actually learn pretty decent representations in a completely self-supervised manner. Autoencoders are also part of that, except that autoencoders don't really learn useful or not really generalizable representations, because their whole objective is simply reproducing the image. And then this phase two, once you've trained this deep neural network, you can apply it to some sort of new task. That's the whole idea of self-supervised learning, that you have a giant data set where you don't have labels, but then you want to do something. So now you've trained your network, and now you want to apply it to some specialized data set where, for example, getting annotations is extremely expensive, or you simply don't have enough annotations, etc. And what you do on these data sets are the following. You can either do some limited fine-tuning. So as we had earlier, you just train a linear layer. And you can do that either in the middle of the network or at the end, etc. I think we had that in lecture 5. Or you can do the fine-tuning. So you just take the network basically as a really, really good initialization. So forget about the Gaussians, etc. This is like the best initialization that you can have in a way if the neural network was trained well. It has all the relevant features at the end, and so fine-tuning becomes extremely quickly and extremely efficient, as we'll see. And this is also related to us humans. So once we've developed the basics of the visual system, I can give you a new task, let's say, or you're then doing your medicine studies, and in a matter of few images, you'll be able to recognize tumors. And so the idea is once you've trained this very generic visual encoder, or very generic any encoder, you can then train it very efficiently. So this is the general procedure for self-supervised learning when we do representation learning. Representation learning is all about getting this pre-trained or getting this encoder, which takes any sort of input and gives you like a vector out. There's also what I like to call a different part of self-supervised learning called useful self-supervised learning. The main difference here is that now instead of having a proxy task, you have a self-supervised learning task. What do we mean by that? You can post some tasks like object segmentation or object detection or speaker detection or dataset labeling as a self-supervised task itself. The easiest example that we'll be looking at today will be self-supervised data labeling. So basically the idea is you simply cluster your dataset into clusters, which are noisy labels essentially. And in that sense, you're trying to solve this problem of labeling a dataset in a self-supervised manner. And with that, you're getting a good representation from your neural network, which is fine, but the main purpose is something else. You're getting like this free labeling of a data set, for example. But yeah, more on that one later. Right, are there any questions so far about what self-supervised learning is? All right, good. Then let's dive into the why. There's a couple of reasons. I've already mentioned this, but here is it a bit visualized. So if you take a look at these images, there are quite a lot, and now there are even more. And if you multiply this by 50, you end up at ImageNet, which is like a standard data set. It's around 140 gigabytes. Everyone sort of in academia uses this data set. And the larger version that some people in industry use is 20 times bigger. Similarly to this clip, where every 90 milliseconds there's an image, if you watch this for, I think, 30 hours, then you've seen ImageNet, basically. So it gives you a bit of a feel that this is quite a lot of images. And if you wanted to label these, it would be quite expensive and would carry all kinds of problems with it in order to label it accurately. And now we know that Instagram has 50 billion images and counting. So ImageNet is in the middle. This is 1 billion. And so Instagram would be 50 times this. So we would probably cover all the walls in this lecture room. And we wouldn't be able to annotate everything, right? But the data sets keep getting bigger. And scale is hugely important if you want to include, if your network should see very diverse inputs. But if you require labels for that, then it's not gonna cut it. Reason number 2 is the constantly changing domains. So if you did your labeling in 72, you trained your car detector, and then you run it in 2012, it probably wouldn't really get it. At least that would be my hypothesis. There's many fast-changing items like phones, clothes, or cars, and they quickly change appearance, and you would be constantly stuck with relabeling new models as they come out. And you also wouldn't know which types of objects or scenes are the ones that need to be relabeled. Except, of course, sometimes you can get a bit lucky if you're trying to detect Lada cars. Really, really consistent. So yeah, again, large costs just to keeping up. So it's not even to get better models, but it's just for keeping up because the society and the data sets are changing. Reason number 3 is accessibility and generalizability. So once you have these strong pre-trained models that are very good at seeing generic features, you can apply them to all kinds of things. So for plant identification, for medical usages, there's papers that use it for archaeology, for cosmic applications. Having strong pre-trained models allows many more people to use these models for their own research, making it more accessible and broadening the impact that these models can bring. And again, this is not only for vision. So you could have a very generic molecule encoder, which not only captures, let's say, the biomolecular structure, but also how it would react in order with like some human enzymes, etc. Ambiguity of labels, the 4th reason. I'm sort of off counting here. If you think about the label a house, like everyone probably has a very different image in mind. Same for a boat. It's not clear at all what kind of system we should label our data set. It's not only clear, but some systems can be very problematic. So for example, you have this sort of labeling system, which I'm not going to read out, but this is from a sort of online dictionary, essentially, and an academic one at that, which simply tried to group all the nouns in the English vocabulary. And of course, back then, like no one was looking at it in detail, and they simply used this sort of dictionary to type the words automatically into a search engine and retrieve images for that, which doesn't even make sense because they're not even visual labels. And like, of course, some of these you shouldn't even have in a data set. And this was actually in the larger version of ImageNet. So labels can be ambiguous at best, discriminating and bias propagating at worst. So if we want just very simple encoders, we ideally wouldn't want to provide these models with such priors. Like, it's not prior knowledge, it's prior bias, basically. So we wouldn't want that. Finally, the last reason, which I've mentioned, I think, a couple of times in the lecture, and which is quite motivating for me, is this idea of that it's somewhat similar to how babies or toddlers learn and how they develop the visual system. So what toddlers learn, or what toddlers see, for example, there's some data sets where they strapped a GoPro camera on top of toddlers, looks quite different from, for example, typical ImageNet images. So it's quite interesting to analyze how far can we go with this. So the question here, the motivating question would be, what are the limits of learning without labels? Like, how far can we actually go? Can we learn how to group all kinds of objects together? Can we track them, etc.? And like, could we initialize a robot in such a manner that it can just keep on seeing new things and learning new things? Any questions so far? All right, so then I'll get you warmed up. So please turn to your neighbor and briefly explain the core idea behind self-supervised learning. You can talk about what the core principles and ideas are, what's intuitive, what is so far unclear. There should be points, because otherwise I don't have anything to say in the next hour. And then also you can discuss what the human learning experience versus the ML perspective is. And yeah, like roughly 2 minutes or so. And again, if you're sitting alone, just turn up to your upstairs neighbor or something. All right, let's continue. Also, I just uploaded the slides. I got the feedback from the feedback session that I should only upload the slides when they're in the final version. And of course, tried to, or like my to-do was to upload it straight before the lecture. Then of course I tend to forget it. But yeah, they're online on Canvas now. So let me know if they're not. But they should be. All right. Were there any questions that came up from this discussion? Yes, please.
Maybe on a map, like where would you put self-supervised learning compared to semi-supervised learning and compared to clustering? How do those all relate?
I would go for the following map. Self-supervised learning, clustering, semi-supervised learning, and something like supervised learning, kind of like this. So typically, you do not use labels in clustering. You can use clustering. Clustering is, in such description, a technique for self-supervised learning. And whatever you do with self-supervised learning, if you incorporate some usage of labels, you can make it in a semi-supervised manner. So there's some formulations also where you do clustering with some labels that you already have, and which improves clustering qualities. But yeah, that's, I would say, a rough map. Yeah, so in self-supervised learning, especially in the representation learning part, here the idea is really the first stage pre-training. And what comes afterwards could be semi-supervised or could be supervised learning, could be anything really. Yeah. And yeah, when you pre-train in a self-supervised manner and then fine-tune in a supervised manner, depending on how you do it, you can call it transfer learning or semi-supervised learning. It really depends a bit. Usually semi-supervised learning refers to it being the same data set, but definitions vary. Yeah?
I don't really understand the whole concept in images for self-supervised learning, like for example for text generation, for the word model, for example.
Yeah.
Complete the sentence. The input data is just, you can always just remove the last word and complete it and you have your data there. So you don't really have to do anything to the input data. But with images, you you can like cluster the images, but at the end, you are going to have to label the clusters manually. So there's still some human interaction that has to be towards the data.
It depends a bit on what you want to do. Just like for words, what you can do in an image, and now the next part will be going about the how of images. If this is your image, right, you can literally blank out this one and let a model predict what is supposed to be in the middle, let it reconstruct it. And this is exactly what these language models are doing as well. Now this model has not that many use cases, it's very rare that you need to in-paint a square in an image. But this model, in learning how to do that, will learn some useful features because it cannot in-paint without understanding at least rough strides of or rough things about the image. But we'll be going to the how next. Another question?
When you are training the model to label images, do you give a set of labels or does the model also come up with the labels itself?
Right.
Because otherwise you're not really removing any biases, right? Because you still give the labels.
Right. The thing about clusterings, especially, you have, self-supervised learning doesn't get rid of biases. That's for sure. It really depends on where your image data set has been captured, and most image data sets have been captured in the global north, mostly in US and Europe. So it still has biases for sure. But then it depends whether you're using self-supervised learning for clustering and then trying to make labeling, for example, more efficient. That can help, that can make it more efficient. But if you're only trying to label a data set, you'll get the same biases no matter what you do. That's a whole different thing about how to not get biases. If you simply want a vision model that, for example, maybe next lecture I'll bring some examples of such biases. Oh, actually we have some in this lecture as well. I'll show you some of these biases that the labels contain. And then we might be able to figure out why not using these labels reduces the bias. All right, so let's dive into the how of self-supervised learning. So we'll only be covering some of the most important works. And yeah, as I mentioned, this was actually from the first lecture, which I mentioned, that we organize these sort of workshops. And yeah, as you can see, these workshops are very much ongoing. So we as academics and researchers meet and discuss these things and discuss what's going on, what developments are there, and what's going to happen next, and so on. And so, for example, this tutorial on the left is fully available on YouTube. If you want to get a more in-depth introduction to this topic, I really recommend this one. If you want to know what are the most recent developments, these workshop series that we've organized, I can recommend. All right, so how do we learn without labels? Well, I mentioned that we need to generate a loss that provides gradients. And the types of signals that we can use are the following. Reconstruction, I've just briefly mentioned that one. Geometry, augmentation invariance, image uniqueness, and assumed structure, which we'll be looking at clustering. And of course, there's a bunch more. These will be the most representative ones. And we start with the one that I already mentioned, context prediction. So as you've seen in NLP, you have the word-to-vec, or even how masked BERT is trained with masked language modeling, where you simply have the context and you need to predict what's inside. A very similar thing is either you predict actually the RGB pixels, or you do the following in the paper called Unsupervised Visual Representation Learning by Context Prediction. So here your model gets a center patch, in this case the blue patch, and it gets another patch. So one out of those remaining 8 patches, basically. And these 8 patches are not directly touching this patch, because otherwise the task would be too easy. So they're like somewhere in a region around this image. And now the model that gets these 2 patches needs to predict where, relatively speaking, is this other patch. So you can see the patch of the ear. And in this 3x3 grid, the right solution would be y equals 3. So this is a simple task. You can see it doesn't require labels. It only requires images. In order to solve it, it somehow needs to understand that ears tend to be on top of snouts, for example. The architecture looks roughly as follows. You have 2 CNNs, which have the same weights. And then you get 2 times the output. And you simply concatenate it and run a classifier on top of it. And this classifier then has a 8-way classification problem. And this is pretty much it. This is an extremely simple and old method, but it was 2015, so it was one of the first self-supervised learning methods. And yeah, this is pretty much how language modeling does it as well. Yeah, there's this example here. Right, so already these old methods were able to learn pretty decent features. I don't know if you can see it here, but you can see, for example, by visualizing the features, that it captures stuff like eyes or stares or even parts of human faces. These aren't the best visualization, I have to admit. But again, these were pretty old models. Following from that, we also had context encoders, which were doing exactly this sort of in-painting task. Also, again, very similar, very much coming from developments in NLP. And also, still pretty early method is RodNet, which is one of the more influential ones. So here, well, first of all, this is a conclusion. In RodNet, you do the following. It's short for rotation net, of course. You have your data set of images, and you randomly rotate them by a multiple of 90 degrees. So you can see the second image, for example, is rotated by 270 degrees, and the other one, the third one, by 90 degrees, for example. And now you simply train the model to predict 1 out of 4 classes, like 0 degrees, 90 degrees, 180, or 270 degrees. And again, you're not using any labels. What you're leveraging is that most people take a picture upright. So most people do not take a random picture with like camera upside down, etc. And by simply leveraging this sort of signal, you can generate a new task, a classification task, which gives you gradients. for free, essentially. Of course, this method, with its simplicity, was like really convincing and was like one of the main papers that made self-supervised learning really popular. But it has its problems. So some images really, it doesn't matter which way is up, and you cannot really tell, like these images. And so it wasn't exactly the paradigm that lasted for a long time. However, if you ever wanted to train something really simple, why not use the biases that you have in your data set? Yes?
In this case, what was the downstream task method? Or was this just of the sake?
We'll talk about the downstream tasks in a bit. But that's an interesting question. So you could actually pose this. So this was mainly used for representation learning. So then you take your model and try to predict, for example, different classes of images. So like Cypher 10, for example, would be a downstream task. But you can use this also as a useful self-supervised learning thing. Just like if you upload your pictures to Google Photos, it will ask, is this image maybe rotated? So actually, something like that is probably happening in the back end, but probably more efficient. But yeah. Question?
In this method, don't they still use the ground truth of what was up?
Yes.
So then it's not self-supervised.
Yeah. That is a good question. What counts as self-supervised or not? It really, you can be a bit nitpicky about it easily, but given that the data comes with the image, I think calling it self-supervised is fine. Just like if you have a video, like an MP4, which comes with the video stream and the audio stream, we call it multimodal self-supervised. It uses another signal as supervision, basically. Here it uses the other signal. I mean, it's noisy, right? Like we don't know exactly whether every image has been shot correctly. So it's not labeled. Mainly, you can get into long discussions if you talk about CLIP, for example, or other data sets which just scrape the internet, so no human explicitly labeled it. So it didn't have annotation costs, but it still has like all the other things. So yeah. But I would go for internet is weakly supervised, and this is self-supervised, basically, as terminology goes. Any other questions? All right. So then we go to this very, very influential paradigm for self-supervised learning called contrastive learning. And actually, before all of this started, there used to be a prior work in 2014 at NeurIPS called Exemplar CNN. By the way, from the same guy who also did the vision transformer when he was younger, of course. So the idea here was you take an image and you augment it a couple of times, and then you have your neural network predict, oh, this is class equals image ID. So let's say this was image 1, then the network needs to predict this is class 1. Then you take another set of images, heavily augmented, and say, oh, this is class K. And you do this for all the images you have. Of course, this doesn't scale very well because the last layer needs to have as many output units as there are images. But the idea is kind of nice because you know the augmentations don't change the class, and you sort of assume that every image is unique. It's an assumption. So it uses image uniqueness as a training signal, and in that manner enforces augmentation invariance because you augment it and you always try to push it again to be the same class. And this is a generic principle. So you assume every image has its own content. Augmentations don't change the content. So let's just predict it to be its own class because we don't know what kind of classes there are. So let's just say every image is its own class. And then 4 years later, this got a bit more popular. So there was a paper called Non-Parametric Instance Discrimination, which then started this contrastive learning era. And the one that's most famous and the one that you will be tackling in this week's tutorial as well after this lecture is SimClear, which basically simplified this even further. So what you can see here are 2 images. Both are augmented. So in the end, you have 4 images basically going in. These CNNs that you can see, they all have the same weight. So it's really just one CNN where you put in 4 images here, essentially. And then you get some feature, and then you apply an MLP, and you get another feature. So far, so good. And what you do next is you now say, okay, the features that originally come from the same image, they should attract. So they should be similar. They should be as close as possible. So if you, for example, visualize this, you would have, for example, on the left-hand side, you get these two features. They lie somewhere on this lower dimensional manifold that we always spoke about. And then let's say the other two features lie somewhere here. And so what do we mean by attract? We now say, well, these guys should really move closer together. And stuff that's not of the same image should move far away. So you have some sort of pushing force here happening. And some of you might already recognize this from assignment 2. This is essentially the same as the CLIP pre-training. Except in CLIP, we were using, instead of an augmentation, we were using the text. And so we can write out the laws now in more detail. It's pretty much exactly as we had in assignment 2, just written slightly differently. You have the contrastive laws for positive pairs I and j, here given by the simple formula of a softmax of similarities. So similarity here stands for the simple dot product. So you take your features. So again, if this was a 2D feature, this would simply be, for example, x11, x12, and this one would be feature x21 and x22. So you can simply do the dot product, and you get a number, right? And this number tells you how similar are they. The dot product is also related to the angle, and that's why you call it also cosine similarity. So you get some sort of dot product here. This is a similarity between the pairs which go together. And you can also get the dot product between, for example, these two. And then you get another value. And you try to basically maximize this value and minimize this value, right? That's the whole goal of contrastive learning. And because this is not very easy, you're using this temperature parameter that we all love. So the temperature parameter scales the softmax. It basically simply multiplies the values, the logits, before you apply the softmax. So if usually you would have this kind of distribution, if you use a high temperature, it will peak because the high values will get exaggerated and the low values will get even lower. Oh yeah, and we call this one the non-parametric softmax. And this is quite a useful trick, generally speaking. So usually we're used to softmax having a last layer which has, let's say, n classes, right? And then we apply a softmax. However, what we're doing here is we're applying a softmax across dot products. And these dot products are simply generated by some sort of features. And so this is something that takes a bit to wrap your head around, that we're doing a softmax without having a fully connected layer, essentially. But the principle is as easy as I stated here, basically. And so what we have here is we're enforcing image uniqueness, and we're enforcing augmentation invariance. So we're forcing the augmentation invariance by saying this first dot product should be high, and we're enforcing that was augmentation invariance, and we're enforcing image uniqueness by saying that the other dot product, the one which contains two different images, that should be low as possible. And yeah, you can see the similarity here as well. So in the clip illustration, you have all the matching dot products on the diagonal, essentially. Yes?
Can other metric learning measurements be used for self-supervised learning, like center loss or something like that?
There is a bunch of metric learning approaches. So you could design all kinds of things, and before contrastive learning came along, there were also other approaches. Margin losses would be one thing. I'm introducing only contrastive learning here because it's extremely simple, works often out of the box, and has been the most influential. So after this became popular in images, it really took off. So it's now everywhere. It's in graphs, it's in videos, it's in, you name it really, even in NLP. So it went, so self-supervised learning came from NLP, we developed contrastive learning sort of, and then it went back to NLP, and so contrastive learning is and was highly influential. Besides the SimClear work, there's also another work which was quite influential, which introduced this idea of momentum encoder. So in this case, what we had before, we had our CNN here, or nowadays you would use a vision transformer, I suppose. And you got these two representations. And all that MoCo, momentum contrast, did was essentially, instead of encoding these both through the same network, they encoded the other view, the other image, the other augmented image, from a different network. So you still had your one image, which generated two augmentations. And one went through this network and one went through the other. And same for the images from the other encoder. And this other encoder, of course, it cannot be a drastically different encoder because otherwise the dot products do not make sense. So this momentum encoder actually has this extremely simple formula. So if you look at the parameters of this encoder, they are simply computed by this one line update. And you can recognize it as a momentum update. So basically, and that's why it's called momentum encoder, you have an encoder which gets updated via gradient descent. This is this one. Let's call it phi. And then this one updates the weights of this phi exponential moving average in a slow manner. And this has like really good regularizing properties. And it might seem somewhat arbitrary, but exponential moving averages, I mean, starting from Adam and all of these optimizers is like one of the things which almost always improves performances. One of the reasons is because optimization generally jumps around heavily. This one basically stabilizes it. But there's still no clear theory why making everything exponentially moving average improves everything. But basically, SimClear and MoCo marked the start of large and industrial self-supervised learning, which, as you can see, both heavily rely on having two image augmentations. If in SimClear, the previous work where this was the same network for both, if you didn't augment, if you simply put in the same image, you would always get as dot product 1, because you would just get two identical features, so you wouldn't learn any meaningful features apart from pushing away everything else, but that would also be very easy, because if you always compute a 1 for your own dot product, the rest is not going to be 1, so it wouldn't be much of a learning signal. All right, and now it's getting funnier in self-supervised learning, where we are also incorporating more and more of tasks that originally come from NLP. For example, instead of simply predicting this context, we simply mask out multiple parts in this image and let it predict exactly those parts. And this is now exactly like masked image modeling. So it's called masked language modeling. So it's called masked image modeling now. And is exactly how BERT was, for example, trained. So we are almost back to NLP in some ways. But the jury is still out there whether this is actually a meaningful approach for modeling images. Because as compared to language, these patches don't have initial meanings, right? Like what we're masking in language models are, for example, whole words which have meanings. In images, might not make that much sense. Question?
When you say predict, you're referring to the pixel values?
Yes, when I say predict, I refer to the pixel values. There are some variations to that, though. So there are works based on this for videos which do not predict pixel values, but instead, for example, gradients. Because predicting pixel values, as you might have seen in the third assignment, is sometimes not so easy, especially once it goes to larger scale stuff. All right. Then we come to clustering, which is sort of, besides contrastive learning, there was always this other main domain of clustering as self-supervised learning. And so there was this work, Deep Cluster, there's Sela, which we're going to talk about in the second half of the lecture. And then there's online clustering versions and Dino, which we're all going to talk about in the second half of the lecture. So let's have a quick break. Let's take 10 minutes and be back at 5 to 4.
still just aim with so many samples. Also now I'm making so many samples and then run this with the code. Actually get this
All right, let's continue. All right, so someone asked me in the break about the difference between self-supervised and unsupervised learning. And I expected this question much earlier, actually. So there isn't a clear definition. What most people will tell you, including myself, is that unsupervised learning is mostly about finding structure within the data, so PCA, and also just simple clustering and stuff like that would be falling in this older term of unsupervised learning. Self-supervised learning is more like learning something that then works on other data sets. That's, I would say, I would go for this definition. Sometimes you see many people use this term interchangeably, though. All right, so we talked about the data sets. And this is now somewhat image-centric, but it will hopefully also give you a view of the sort of problematic side of data sets that we've already hinted at in some lectures. So up until now, and somewhat still, the standard is to evaluate and test self-supervised methods on ImageNet, which is extremely strange because ImageNet is a class-balanced data set, so every class has the same amount of images. We know the labels of the images. They are obtained via a search engine. The license is not clear. The people didn't consent to being in the data set. It has more than 120 classes of dogs, and ImageNet has 1,000 classes with 1 million images, so that's around 12,000 images of dogs. So that's not 12% of the world is dogs, which is not representative, I think, for most people at least, which is weird. And not only that, there is research from not only Crayford and Pagelin, but also Prabhu and Birhane in the FACT conference, which investigated the problematic images in these data sets. So I've mentioned this search tree that they used for figuring out images. They also used some automated methods to look at specific ImageNet categories. So for example, what they found is that a model which was trained to predict whether an image is not safe for work was heavily active in those particular ImageNet class categories. And not only that, but you find extreme biases in the depictions as well. So if you look at, for example, the co-occurrence of the class harp with the gender that's being identified by this automated model, which of course can be problematic as well, but here they use it for automatic analysis, so okay. And you can see that, for example, harp almost always occurs with a woman in the image, while for some reason a cornet and saxophone always appears with a man. So this is extremely strange. And there's another work, I can link it to you, which shows that actually if you simply increase the amount of data you use, if you instead of using 1 million, use 10 billion, so it's research from Facebook, where they used Instagram data, you can actually significantly decrease the biases. Because then the model will have seen enough female saxophone players or men harpists that it wouldn't associate one with the other. So it learns to decorrelate these things. And what we did when we saw this sort of research, we had this other idea of how about we just remove all the humans? I mean, why not, right? It's self-supervised learning. It's not trying to learn anything human-specific. It's trying to learn is these features like eyes, ears, shapes, and stuff like that. So what we did is exactly that. We created a data set which has these sort of images. It's a bit low quality here, but this, you can see it. And you almost really always expect a human to be there because they look so diverse and it's exactly what we are sort of used to. But in fact, there's no single human in that. And we used like some automated pipeline as well as some human verification that there actually wasn't a human in this data set. And we called this data set PASS, and it's got random images, so it's a good baseline for evaluating self-supervised models. It's got licenses. And because there's no people or signatures or stuff like that, it's safe for GDPR, which is becoming more and more important. And importantly, it works the same as a pre-training data set as ImageNet in terms of how well the features are. And this gives an overview of what kind of evaluations we did in this paper, which are also the most common evaluations that people run if they want to develop a new self-supervised learning method. These would be, for example, simple clustering and then seeing do the clusters match with what the labels of this data set were originally for. And so it's a completely frozen evaluation. You don't change the encoder at all. Or you can simply use it as an initialization and then fine-tune the whole model. So here we tested, for example, Microsoft Coco, Pascal VOC, and Elvis, which are all data sets for object segmentation, etc. And importantly, even if the data set downstream was something like dense pose estimation or key point detection, where you need to find key points of human, it performed similarly well. So the model, just by seeing these sort of shapes and statues and maybe apes and stuff like that, it has seen enough things that it can then quickly fine-tune for human detection. Right. Downstream semi-supervised, so I've mentioned this here. So once you've done self-supervised learning, and now you want to do some fine-tuning, self-supervised models work extremely well. So once pre-trained, you can train self-supervised models for a new task with only very few labels. So here, our supervisedly trained ResNet is compared with a CPC, that's the C stands for contrastive, another contrastive self-supervised learning method. And you can see that in this few label regime, where only you have, for example, 1 or 2% of labeled data, you achieve significant gains in terms of final performance as compared to if you use a supervised ResNet. One of the main reasons is that supervised networks tend to remove all the features they don't require for doing classification. So if you can classify a dog simply by this one texture, then it wouldn't care about all the other things. Contrastive tasks, they often, for example, compare all the images with all the other images, so it needs to keep much more information in the encoder. So that's one reason why these methods tend to work better. And of course, this is extremely interesting if you were to found a startup and tackle a new problem, because often you wouldn't have a huge labeled data set. All right, so now we're going to talk about one method in detail, which is optimal transport-based clustering. And it's a paper from mine, which we presented at ICLR 20, which is somewhat old now, 2 years, but it's still relevant, actually. And of course, you don't have to remember all these details for the exam. So everything that's very much paper-oriented, you don't. Standard things like what are augmentations, what's the contrastive loss, this, I think, is fair game. Yes, question. That was a really quick...
You're mentioning that for startups it's good that you can use self-supervised learning, but doesn't it require, because you're dealing with way bigger data sets, it actually requires such a large amount of compute to run these models that it's actually unfeasible for a startup to actually use self-supervised learning in that manner?
As always, the question is sort of, or the answer is sort of, it depends. You can start with very generic pre-trained models like CLIP. I mean, CLIP is technically not allowed for commercial use, but you can start with these large models and then fine-tune. You can also do you can start with these large models that were trained from industry and then do another round of self-supervised learning on your own data set, which then doesn't require all that much time. Let's say you're producing watches. You have like 50,000 images of watches, out of which 1% of these are labeled. So we would first adapt your representation on this domain of watches by doing some sort of self-supervised learning. And then you fine-tune it finally using the labels. So that's another approach, how to use self-supervised learning to get closer to the domain while using all the images you have, basically. All right, so this work, we go back to this idea of, well, self-supervised learning is just supervised learning without labels. So this is a lot of images, and this times 50 is roughly ImageNet. And what we want to arrive at is basically this categorization. So we can call them concepts or clusters or labels, pseudo-labels, whatever. And we want to go from from left to right. And of course, this is somewhat of a chicken and egg problem. If we had a good chicken, for example, a good model, and then we can simply go over the whole data set and always pick the argmax prediction, and we get a decent labeling out. Similarly, if we have the labels, of course, we can simply train a model and all is well, right? But how do we solve this chicken and egg problem if we have a network which is randomly initialized and we do not have the labels? And this is the problem that we were tackling in this paper. And the answer is augmentations. Yes. All right, so what are augmentations? Let's first take a bird's eye view. So I'm writing here the key to image understanding is separating meaning from appearance. Well, what is appearance here? We have this image of a tree, right? And these are really just RGB pixel values, somewhere between 0 and 255. Now, if we apply augmentations, these values will drastically change, like extremely, a lot. However, for us humans, it's obvious that nothing really has changed. Okay, it's slightly brighter, but this really doesn't change any meaning of the image usually. Same for mirroring the image or for zooming in differently. And if they don't change, if these sort of transformations do not change the meaning, we typically call them augmentations. And we're going to be leveraging this fact in this method, again, for self-supervised learning. But before we do that, a quick quiz. What other ways of incorporating prior knowledge have we already learned about? I'm writing multiple choice because potentially it's multiple choice. It doesn't mean that it's multiple choice. Because in the past we had some things which had two answers, right? So is it A, or 1, choosing the right learning rate, 2, setting the network architecture, 3, picking the optimizer, 4, choosing the number of epochs, or 5, choosing the loss? All right, have a think. Right, on the count of 3. 1, 2, 3. Right, I'm seeing 2, 2, 5, 3, 2, 5, 2, 2, 5, 2, 5, 5, 5, 5, 2. Okay, lots of 5s and 2s, and some 3s. All right, yeah, 1 is not. That is very true. 2, very much true. Like, for example, in a CNN, right, we're saying that it doesn't matter whether a dog occurs in the left side or the right side. We're sort of having this thing that the equivariance hypothesis, or for supervised learning, that you simply apply the same weights everywhere, right? You could have completely different architectures where you say the left side has one set of weights, the right side has other set of weights. Picking the optimizer, I wouldn't really put this into incorporating prior knowledge, unless you very, very specifically think that a particular optimizer will find a particular solution to a problem. I wouldn't really call this incorporating prior knowledge unless it's a very particular case. 4, I think no one has raised their hand for that, which makes sense. It's sort of the same thing as number 1. 5, very much so. Like if you have a contrastive loss, you're really putting in this assumption that every image is different from every other image, which will be violated if you have duplicates, for example. Or in RodNet, you're assuming that every image is upright and that you can determine it. Or in the loss function, you can also smoothen the labels, as we had discussed. That's another assumption, for example, that, the labels aren't extremely accurate. Any questions? All right. So on the high-level idea, I said we're going to use this idea of augmentation invariance. What we do is we start with assigning random labels to images, as we do here. For example, this image gets label A, this image gets label B. And then we augment the images and see what kind of labels does our network predict. And if it gets it wrong, just like it does here, we try to make these assignments consistent. And we do that such that we can now say, after this whole procedure, which I'm going to talk about, that image 1 belongs to label A, and image 2 belongs to label 2. Image 2 belongs to label B. Now, what we did in this paper was we took the standard cross-entropy laws that you should be able to recognize here. You're trying to find the parameters phi for a network, given some labels y, and it's simply the cross-entropy laws across the whole data set. This we want to do, except that we don't have y. So what do? What we did is first we said, well, these one-hot labels are really tough to optimize. Let's just say it's an assignment table instead. So instead of having this one-hot vector of y, which has, for example, the entry 1 or 900 or 500 or something, we're going to say instead this one would be, for example, n by 1, where n is the dataset size. We're instead going to say, okay, the labels can be soft. So this is, for example, n by 1,000 instead. This was the first step. So this makes it much easier to optimize because optimizing integers, no way. But this one gave us very bad solutions because it's very easy for the model to just give every image the same label. What we then did is we had this additional assumption where we say every pseudo label needs to occur an equal number of times. We can simply say that. It actually, in the end, acts as a regularizer if you write out the formula. But just by saying this assumption, we can now pose this whole thing as a as a clean mathematical problem called optimal transport, which, as it turns out, we can optimize extremely quickly using matrix multiplies, which, of course, our GPU is very happy about. Obviously, not needed for the exam, but on the internet, you cannot really find the whole derivation, so I put it in here in case someone is interested. And yeah, it's pretty clean mathematics, and you end up with a nice formula that you can optimize. So the overall algorithm, given this sort of thing that we called optimal labeling, you start with a randomly initialized neural network. You do this, and you get some sort of assignments. They're not great, but they're good enough. And then you train the neural network with cross-entropy to respect this augmentation invariance. And you go back and forth. So it's kind of like an expectation maximization algorithm. And with that, we've also solved this age-old mystery of what comes first, the chicken or the egg. It's, yes, randomized chicken, always. All right, so if we apply this method on ImageNet, these 1.2 million images, we, for example, get this cluster. So this cluster, pretty straightforward. It's that of a geyser. Same for the zebra cluster or butterfly cluster or ball of hay cluster. You can see they're pretty good. We can actually check how well they match with the ImageNet annotations. So again, ImageNet, it took more than 2.5 years of work and extreme amounts of money to actually label the data set. But since back then we simply ran our method on this data set, we can also compare it with this label. And you can see that it matches pretty well. And of course, these are picked to match well as well. That's why they're in the slides. But we also released all the clusters online. And if you click through these, you can find some clusters which are not as pure as this. So they will have more colorful borders. But what's really interesting is you can find some of these clusters still making a lot of sense. So you will find a cluster with like people in forest. And some ImageNet labels would be cycling. Some would be dog, because there's a dog. Some others would be forest. But to us, they all look pretty similar. And so it really is a bit of a difficult domain because, yeah, you can only evaluate it against some labels, but they still make sense. But there's some other research that goes into how interpretable are actually these clusters that the neural network finds on its own.
You do not specify beforehand the number of clusters, right?
So in this method, you have to specify the number of clusters. It, however, doesn't really matter how much you set it to. Like, you can set it to 5,000, 10,000, whatever it is.
But what was the relationship between the number of classes and the number of classes of images?
Yeah, so ImageNet has 1,000 classes. If you want to identify exactly those, then yeah, maybe setting it to 1,000 makes most sense. But in self-supervised learning, you usually don't know how many classes you have. So we simply ran it with some high number. And the thing is, if you pick a high enough number, if, for example, this was your original ImageNet classes of dogs and this your original ImageNet classes of cats, if you pick a high enough number, then okay, your dog class gets represented by 4 clusters instead, and there's no real problem with that. You can actually then merge these clusters using something like hierarchical clustering to then end up at a lower number as well, if you wanted to, but that's another story. The main work, well, here we have this sort of meaningful and nice way of visualizing what the network is, the network is interpreting the data set basically. But we also evaluated it in a more classical way, these ImageNet linear probes that we discussed in lecture 5, where you simply keep the network frozen and then train only a linear layer, for example, after the 4th convolutional layer or the 5th convolutional layer. And I'm not going to go into the details here, but we achieved SOTA, which is, of course, the important keyword here, state-of-the-art performance. All right, so from this work, let's take sort of 3 core takeaways. The first one is invariance to augmentations. Extremely useful, extremely common for all of self-supervised learning. Second one is this virtuous cycle of labeling and representation learning. Not only do these gradually improve each other, but also once we have the labels, they can be easily saved. They can also be used and analyzed to figure out how the network, how the model is basically seeing the data. And there has been some follow-up works also from our lab that look into these. And then this whole idea of balanced pseudo-labeling using optimal transport, using synchron-knop. That's how the algorithm is called. And actually, based on this one, there has been 2 large works, follow-up works, not by us, but by Meta or Facebook AI, which basically first generalizes this to simply cluster not every epoch, but does it within a batch instead, and led to big improvements. And then Dino, which we're going to talk about in a bit more detail, uses the same idea, but instead of using synchron-knop, it applies a slightly different procedure. And yeah, 2 tables from each paper. So for example, Suave uses the algorithm from Saylor and gets strong performances by simply training longer and stuff like that. And then Dino pretty much gets the same performance compared to the centering operation if they simply use the synchron-knop. Now, about this Dino. I showed you this in the Transformers lecture. And Dino is quite remarkable. It has this simple pre-training objective that I denoted here. So again, you can see this EMA, that's the exponential moving average. And then apart from that, it's basically doing some sort of clustering. So again, you have these 2 views where you have x is augmented once and you get x1, and I augment it another time, you get x2. And the rest is pretty much the same as we had before. And by simply training that on a vision transformer and then looking at where does the CLS, the attention value of the CLS token with the other spatial patches, you get these really nice looking maps of the salient objects. And this is in stark contrast to when you do supervised training on vision transformers. So here in the top row, you can see what happens if you visualize the same sort of attention but with a supervised model. And you can see it, I think, here best for the train and the motorcycle. It's sort of all over the place. But if you train it in a self-supervised manner, it really ends up focusing on the object itself. And not only that, but these features from Dino have been used extensively for all kinds of other things. So these sort of features generalize even across categories. So you can see these, you can do something called co-segmentation. And for example, the features of the head of a bull versus the head of an elk ends up being the same. So it can identify parts across 2 classes as well. And this really opened up a whole domain. And this is also the model that Andrea used for reconstructing 3D objects in a semantically meaningful way in his lecture. Any questions for that? All right. All right, so then we move on to the not last one, previous to last one, how research gets done mini-series. So we're at part 9. And here I have Professor Fraser Stoddart here with his quote, "You've got to break the rules." He got his Nobel Prize for the synthesis of molecular machines, and he was in an interview writing that he liked rebelling against the hierarchical system of academia and always had an open door policy. And He was also one of the first research to make extensive use of color in chemistry publications, which completely changed how chemistry papers were written, apparently. Just as a brief note, it's always good to break the rules. I think that's a great idea. All right, and for research, of course. So right, the previous parts, I'm not going to read them again. There are a bunch now, but last time we talked about the importance of oblations and always varying one thing at a time to properly understand what's happening. So ideally, before or even while doing these last steps, we should be thinking about developing a storyline. And why a story? I mean, we're thinking about communicating our results. We should be writing a hard, cold, and scientific paper, right? But actually, communication in general, and especially science communication, really isn't all that easy. So there's this nice model, there's better models or more scientifically grounded models, but there's this model, if you're the sender of a message and you want to get something to the receiver, there's a bunch of things that you need to consider apart from this factual information. So whatever you write or talk has some self-revelation, has some appeal to the receiver. And of course, you need to keep in mind the relationship and the prior knowledge of the receiver. So communication is really, really tricky. There's a reason why there's a whole discipline. And if we want the receiver to actually understand what we're doing, we need to put in a lot of work. There's actually not a proper English word for this, but in Dutch it's called rode Draht, and in German roter Faden, and in English something like overarching motif. You need to have that in your paper. Basically, that's the story, that's the one thing that the reader will remember in your paper. And for this, that's again, as always with this research series, my personal recommendation is to use Google Docs and don't try to make this thing super nice. Just reiterate it from scratch multiple times. Yeah, you can see it. So for example, here is some screenshot, not to be looked at in detail, but for some experiment sections. So we have the story, automatically finding labels in video dataset doesn't come for free, but it is important. We present a method to do unsupervised video dataset labeling. And we analyze the method and we do this kind of stuff. Actually, the same for a presentation. So slide 1, we talk about what we do, and slide 2 is we present this and why it's important, and so on. And these can be simple bullet points, and you can make them, and then usually the best thing about them is you discover that in order to convey the story nicely, you're still missing some experiments. And once you've done that, you have also the added benefit that you have a really nice introduction for the paper when you're done. All right, any questions? Cool. All right, so we're going to talk about very roughly another paper of ours. So I've mentioned ImageNet. ImageNet has, some of the images have bounding box annotations. And if you simply take the center of this bounding box, so you take the bounding box, you try to balance it, and this is the center where you can hold it on one point, and you visualize these points, they end up being all in the middle. So what does it mean? ImageNet is a very object-centric data set. So the objects depicted are very much in the center of an image. However, the real world might be looking more like this. I mean, it didn't snow that much yesterday, but something like that. And so there's another data set, Microsoft Coco, we mentioned it for segmentation, which has much more balanced segmentations, etc. And this is also something that a robot might encounter, or that we want the learning algorithms to be able to learn from in general. So we presented this work at the last CVPR conference. Adrian was a master's student of mine, where we basically get this sort of output in a self-supervised manner. The overlay isn't super nice here, I have to admit, but you can see, for example, that these people, they have the same color, so that's our pseudo label, so pseudo cluster or cluster basically. So we're basically doing clustering on a spatial level. And without anyone telling the algorithm what people are or whatever it is, it finds consistent clusters for these pixels belonging to people, and it finds some classes belonging to cars and cows and stuff like that. And bus is a different class for car. in this case. Because these methods really aren't perfect, and you can see they're very noisy. But this was one of the earlier works that are moving from image level to spatially dense learning. So we had, So previously, mostly we were talking about a CNN, right, or a vision transformer. And for the CNN, we were always applying this global average pooling, which then gave us like this simple feature vector for every image. And in spatially dense learning, here, I found it. In spatially dense learning, what you do is instead you take this whole feature map, which is, for example, 7 by 7 by 2048 for a ResNet 50. And in spatially dense learning, you want to do something with this map. Let me draw it like this. So you don't want to apply the pooling operation. And the same goes for vision transformer. You don't simply want to do something with a CLS token, but you want to do something with the whole spatial patches. Why do you want to do that? Well, not only because it doesn't make sense to do something with one representation on an image if there's 3 different things depicted on an image, but also it works better on data sets which require these dense segmentations, these dense feature maps. So for example, if your data set in the end is about detecting or segmenting individual pixels, then it makes sense that the pre-training tasks should also be in a spatial manner, so not on an image level. And so we proposed this modification of SWAV. Basically, it's still doing clustering, but it's not doing it on an image level, but on a patch level. So image patches is a key thing. So basically, this one would have 49 patches at that point. And we basically do clustering on that. And we apply some nice things. The main thing is that we, again, crop the image twice. And because we know where the crops are from, so imagine this is the image. And you crop the image twice, right? And there will be some overlap. And we can actually know this overlap because we are the ones that computed the crop. So we can now morph these 2 features. We want these 2 features to be the same, even though they went through a different forward pass in the network. Because, yeah, this one went through the network and this one went separately. We can now say they should be the same. And what we use here is the ROI ROI align operation. And the question is, let's see whether I know I didn't specify any details, but this is more or less a recollection of the lecture where we talked about this. Why might we have used ROI align and not ROI pool? Is it because ROI align is faster to compute, or ROI align can take care of non-rectangular selections, or ROI align works for non-integer locations, or for ROI pool would have worked as well, actually? Anybody not remember what ROI pool is? Okay, some are honest. Very good. All right, let's see. Maybe you can still guess it correctly, though. All right, 3, 2, 1. 1, 1, 2, 2, 2, 3, 3, 2. Right, lots of 3s, I think, and some 1s. ROI align is generally not faster to compute. So I should first say the correct solution is 3, because indeed ROI align works for non-integer locations. So if this is, for example, if this selection was sort of in between grid points, then we don't want to squash this stuff, while ROI pool always doesn't take into account this distance to the center of the pixel. That's the main thing. Regarding number 4, maybe we actually didn't do this experiment. So yeah, that's one thing that we realized after writing the paper, that yeah, actually we didn't. Well, ROI line definitely makes sense because it's more accurate, but we should have tested ROI pool as well, because sometimes taking the simpler approach does make sense. Does make sense. That's not doesn't make sense. All right, so if you simply do this pretext task, which was dense spatial clustering, you sort of get from these starting cluster maps, which look like this, you get to something that looks a bit better already. And now we added a bunch of things. One of the things, let's see, yeah, I'm not going to go into too much detail here, but once you do this, you end up with the bottom right. And this is sort of the final result. You can get from, you start with this Dino pre-trained model. We start actually with a pre-trained model, and then we fine-tune this pre-trained model further using only self-supervision. And then we get these sort of features out, which you can visualize, basically. And these features, again, reached high performances on some standard benchmarks. I'm not going to bore you too much with these. The nice thing sort of that we saw is that with our method, which is meant for these dense images, we actually saw that if you pre-train on a data set which has more content per pixel, it actually does work better on all kinds of downstream data sets, which is rare because what most people, most previous papers at least, saw is that if you pre-train on ImageNet, you tended to get the best performances. No one really knows exactly why, but this is slowly changing. So nowadays, training on COCO, which is this more diverse, more dense image data set, tends to work better. All right. So, yeah. Note here how we used augmentations in Scala, where we said we want augmentation invariance. This will help us solve the chicken and egg problem. And how we used it in Leopard. I know I didn't give too much details, but we used the crop locations. So here we used it not necessarily as invariance, but we needed to have the crops location to then be able to do the ROI pool. All right, any questions so far? Yes?
You just said that most pre-trained models on ImageNet work generally better.
Mm-hmm.
Doesn't it also depend on the benchmarks we are using? If we maybe change a benchmark that has less object-centered pictures, then maybe a pre-trained model on COCO works better.
Yes, yes, very true. Indeed, it heavily depends on what your downstream data set is. It is somewhat problematic that lots of image downstream data sets are very object-centric. That's true. However, despite that, there is still something that one isn't entirely sure why ImageNet works well. It might actually be the 120 dogs, basically, because that makes the task very difficult. So even trying to solve the SimClear task means you need to be able to differentiate really closely similar patterns. And that makes a data set a tricky thing, which is great for learning stable or robust representation. However, for example, the CLIP model, which was trained on 400 million image text pairs, is better in almost every way when you compare it on robustness benchmarks, on image object-centric benchmarks or dense benchmarks. So more images is even better. So yeah. All right, let's continue. So we're going to investigate these augmentations a bit more detail because I find them really interesting. And so what I did in my PhD is the following. I compared this ImageNet data set with a data set of 1 million crops of a single image. So, of course, first of all, this is a weird thing to do. So, but before we talk about why one might do this, let's talk about the process really quickly. So we simply apply an augmentation 1.2 million times on a single image. In this case, the single image has plenty of content inside, so like at least we get some diversity. And then we save the data set. So basically we have a data set of 1.2 million images, crops, saved, and then we can apply an off-the-shelf self-supervised learning method. And back then we used RodNet that I've introduced to you, Deep Cluster, which was a clustering method, and ByGAN. ByGAN was a precursor to the big ByGAN that we mentioned in the GAN lecture. And then we're simply gonna compare, like, how much is this method that was trained on a single image lagging behind. So we can learn basically how much one image can take us from a random initialization. Like, how good is it compared to a random initialization? Because one image is very cheap, but it already contains some information about the visual world. And then the question to us was, okay, how much more than that does self-supervised learning do? Because with one image, we can already incorporate all the information about augmentations, right? So does self-supervised learning at that time incorporate all those 999,000 images in a meaningful way? We tested these 3 images back then. A and B are crowded, B is a drawn image, and C is actually not very crowded at all, and was like a nice contrast to these other 2 images. First, what we did is we applied these methods, again, ByGAN, RodNet, deep cluster, on image A, and we can see that it already is learning very meaningful conv1 features. So this is simply an AlexNet, so you recognize it. On the left-hand side, you can see the filters, the conv1 filters obtained in a supervised manner. And you can see that, okay, the RodNet ones look slightly more color blobby, but the ByGAN one, they very closely resemble the ones from the first conv layer. But of course, we need to quantify this. So here I show you the performance at each convolutional layer from 1 to 5, when testing how well the representations at that layer linearly separate the ImageNet classes. So we're going to train this linear layer, this linear probe, to the ImageNet classes. So of course, the model which was trained on ImageNet will have an advantage, but that's fine. So first, the yellow numbers is a supervised benchmark. And we can see that it steadily increases as the representations go deeper into the network. And in gray, we show the numbers for the deep cluster method, which was at the time the best method available. And you can see that the methods, that the deep cluster objective gets the best representations at conv3, and then the features sort of get worse after conv3, which basically meant that the pre-track task of deep cluster at the time with that network wasn't very much aligned to the task of supervisedly classifying ImageNet labels. Now, let's add the randomly initialized neural network here. So this is if you just have a randomly initialized AlexNet, and then you train a linear probe on top of that. And you can see that at the best point, it achieves 17% top 1 accuracy, which is not too bad. So you can see that even a random network can extract some useful features on which you can train a linear classifier that can accurately predict about 17% of the images. Now, let's add our one image trained network here. And we can see now that it basically matches the performance of the 1 million images method for the All right, test. All right, cool. Yeah, so on conv1 and conv2, one image is good enough, is as good as having 1 million images. And on conv3, well, we get about the same delta that we get when moving from 0 images to 1 images. We get when moving from 1 image to 1 million images, which this makes one realize that self-supervised learning at that time was mostly about learning augmentations, which could be captured in a single image already, plus the augmentations, and we weren't really leveraging those millions of images that well yet. All right, so back then, what was really whatever sort of the chat GPT of the time was style transfer. So what we also did is we took the network and did style transfer. So if you take a supervised network, you get that stuff on the right-hand side where you simply transfer the style of that painting to the content of that image. And for that, you need pre-trained models as well. And you can see that our model that was trained on this ByGAN objective actually does a pretty decent job of doing the style transfer. And we can also do the style transfer on this image that we use to train the network, using that network and so on, and you get these sort of nice representations out. All right, there's a small update that actually we haven't published anywhere, but we actually used also the same data set and used this more updated MoCo objective. And what we found is that actually you can get a decent boost compared to the random initialization of 10% mean average precision when you simply use this data set. And almost very much surprisingly, and using the same protocol as a comparison method, we got within 3% of the MoCo V2 performance, which used, of course, the full ImageNet. And yeah, same for another task of surface normal estimation, where you have a data set and you need to estimate where the surfaces normals are, so where the orthogonal vectors to the surfaces. We're actually training on one image ended up being better than if you train on the whole ImageNet, which is very interesting. And yeah, we also have a recent preprint which sort of takes this learning from augmentations to the next level for those interested. Question?
What does it actually mean to train on one image with all those augmentations? Isn't it always just the same label?
Well, it depends. So for the deep cluster method, where you're clustering the data set, you're basically clustering patches of the data set. So we ran it out of the box, which meant we were clustering this data set of 1.2 million patches into 3,000 clusters, which sounds extremely strange, and it is, yes. So same for the GAN. So we trained a GAN on this data set of 1.2 million patches to create new patches. And indeed, they were looking very much like those patches. But it's funny that it even trained to me. And that was actually the starting point of this whole research. Like, the starting point was, oh, GANs are all the rage at the time. Can we actually train them with a single image? And yeah, that then developed into this whole other part.
I was wondering what is the difference between the images that you took. So you gave the example that you started with 3 images.
Oh, yeah.
What are the performance differences?
Oh, yeah, good point. I forgot to mention that. The surprising thing here was it didn't matter. So it didn't matter at all. The performance was extremely close. So even if you took this San Francisco bridge picture, which doesn't have much content, the performance was basically the same. Which is surprising, but again, it wasn't about the picture itself, but about the augmentations that were giving the learning signal. In this work, however, the choice of image matters a lot, but I'm not going to talk about this one here.
I'm especially interested in the surface normal example you gave. Did that also work for the synthetic image that you, or the drawn image that you took? Because I feel like that.
I think we haven't tested that task with that image. I think for the surface normal, we use this dense city image, basically, but yeah. Yeah?
In the style transfer example, like results,
Mhm.
how do you measure that one method is better than the other?
Yeah.
Or is it just a visual?
Yeah, that was basically just the last half page of the paper, where you then add some qualitative analysis quite often. In this case, yeah, qualitative. We didn't evaluate this. I'm sure there is a metric on how well content is preserved versus style is changed, but yeah. All right. So the conclusion from this was basically self-supervised learning works to a very large extent thanks to augmentations. And this is, of course, what other papers have found as well. So sorry for the weird animation order. On the left-hand side, you can see a snippet from the SimClear paper. So this is this paper which uses the same encoder here. And what you can see is that the choice of augmentations matters a lot. So you can see, for example, in the first row, if you combine crop with color augmentation, you get 56% performance on some downstream evaluation. If you, however, combine this crop augmentation with a rotate augmentation, you only get 30%. So the choice of augmentations matters extremely for the performance of these methods. So you cannot pick any augmentations. It really matters which augmentations you pick. And there's a sort of sweet spot, and that's sort of depicted here on the right bottom half, that there's a sweet spot of how heavily it should be augmented, because if you don't add enough augmentation, there won't be enough signal that the method can learn from. For example, if the overlap between two images is like 99%, while there's not much the model needs to learn from. However, if you apply, for example, heavier augmentation, then it needs to learn, oh, okay, now I'm seeing the right half of the dog and the left half. Oh, but these are actually meant to be the same, and so that's great. However, if the augmentation is so heavy that you end up only seeing the grass floor and the ear of the dog, then you have too much noise, and then the model also cannot learn properly. So this really this goes to the whole theme of why deep learning is very, very engineering heavy, and why some of these things are not really, don't have much of a theory. I mean, this intuition part here looks like it has some nice theory, and we can write it as an information and so on. But in fact, in the end, it's all experimentally validated, and you cannot really make a theory, because you cannot really say how much information is in an image. And the top table basically also shows that the main difference or the main performance gains is in self-supervised learning if you train longer and if you apply better augmentations. All right, so the summary for today's lecture is the following. We talked about why do we want SSL, what is self-supervised learning, what kind of data, how can we do self-supervised learning. We briefly talked about self-supervised learning for doing segmentation without any labels. And then we talked about the role of augmentations. And before you leave, I would like to ask you to quickly evaluate today's lecture, because this one is for my teaching qualification, and so I would appreciate it if you give some feedback for that.